asking.
Thank
So
you very
Hal, it's
much.
all yours.
Okay,
Thank
so
you
I'm going
very
to go
much.
ahead and share my screen with you.
You can unshare my screen. Do I
already-
have to? You've
I did
already done that.
I have the power here.
Aha, I see.
So
Yes.
here again, for those of you that just joined us, Jim was just doing a very basic intro. And so this is our 9 to 10 session here. We're going to be sharing the sessions also in the afternoon. Jim's going to continue with some of the more recent work. I'm going to tell you about the stuff that we were doing sort of just before the NIAC report was due. So I was feverishly working in the lab because basically I was one of the very few people allowed in the building. So I literally had the building to myself because very few people were allowed to be on campus, only the absolutely essential workers. I'd gotten in my request really early and the dean had approved it before there was a clampdown. So literally I was about the only researcher in the whole building. So it was nice and quiet. I got some very nice quiet data because none of the herd of elephants walking around as usual. As you may know, so again, welcome to Estes Park meeting. We're actually holding this Zooming from Cal State Fullerton here. I'm just going to go ahead and go straight into my talk, which is right here. So I'm going to be talking about the initial slight adjustments we're making to the Mega Drive, and again, just before, this was just in the months prior to the report being due. So yeah, unfortunately we're not in Estes Park, but I put the welcome bear there just to make you feel at home. Let's go ahead to this one. Okay, so you may remember that, well, may not, maybe not. So we had some problems with our calibration. There were some calibration issues. It was pointed out to me that I'd made a slight miscalculation, in my Mathematica code. It was kind of a really stupid error, which was easy to fix, but it basically turned out that we'd been looking at forces that were 4 times, well, I'd been calculating them 4 times bigger than they actually were. This was some silly little mathematical thing, which got fixed. So sort of moving my cursor around, there's the torsion balance, and we did work out that the actual force was 4 times less than we thought. But then very soon after that, and of course I had that, we had a really nice calibration done by George. In fact, if you look over to here, you see George's calculation, his experiment, and Jose Rodal was kind enough to do the calculation based on the formula that I'd been using, but he actually enhanced it a little bit by taking into account the thickness of the wires and as well. So he did a very, very accurate calculation. I found that this equation itself is good enough. This equation comes from this reference below, Babic et al. Very, very nice paper. Explains very, very accurately how to get forces from the coils. So we literally have this 3-coil arrangement. Imagine sort of north to south attracting, and then the south to south. So the 2 forces basically. So you've got north-south, and then the other ones are repelling. So one's attracting and one's repelling. So there's actually a double force. That factor of 2 is already taken into account in this equation that I've written here. And the equation agrees very, very well with the experiment that George did. So we know that the results from the forced coils are very accurate now. It turns out that after we'd made some adjustments to our torsional balance, this is the original torsional balance, we've actually now put fins on this thing, really large fins sitting on the left-hand side between the magnetic damper and the central column. And that was just for evaporative cooling. So they're rather large fins that will interlock. And I think I have a picture of that coming up, so I'll be able to show you. It changed the torsional. Well, the period actually didn't change that much, but I did have to do a new calibration. And the new calibration was that basically 0.1 volts on our picoscope was giving us about a micronewton. So that was the latest calibration. I'm very sure that that is accurate. I was very, very careful this time with my Mathematica code. So I'm pretty sure that's correct. All the mistakes have been fixed in terms of the calibration. I'm reasonably confident that that's now correct. I also took off the Filtech sensor. This is the Filtech sensor that we use, and I even took off the metal bracket here, which has a shiny piece of tape on it, and you can't really see it, but it's got reflective tape on there. And I actually moved this thing back with a vernier scale to do the calibration. So using our own equipment, not just the calibration that was given to us by Filtech. So I managed to get a very accurate rule as 750 millivolts per micrometer for displacement. So not only can I give you the force very accurately, I can also give you the displacement also very accurately. The period of our balance is about 6 seconds. Again, that was all worked out. I did a mathematical calculation with the damping and allowed it to use the force from the coils to kick it, and then just let it oscillate down, ring down, and then I fitted that with a mathematical curve, and I got the period to be about, well, you can measure the period directly, to be about 6 seconds. Let's see what happened. Oh yes, we looked at vibration isolation. Now, at this point, we were starting to look at different brackets, different mountings for brackets, and also lots of different materials for the washers. So I'll talk a little bit about that. There was some concern that we may be looking at a vibrational artifact. So one of the very first things I did with the vibrometer, our very expensive $225,000 vibrometer, was to Polytech vibrometer, was to shine the thing at the Faraday cage just to see what the motion of the Faraday cage was, and then shine it on the beam arm just off to the left of the Faraday cage. Now, you can see this picture here. You can actually see the laser beam, the red laser beam hitting the Faraday cage. But then I'd also shine it on the arm, which is over here. You can see my cursor. It's over here to the left. And we found that virtually none of the vibration of the Faraday cage was getting to the beam arm. I mean, it was such the frequency was completely different, and the amplitude was virtually nil. I really had to search around for anything at all that was an amplitude. It was almost like background noise. I really couldn't tell when the device was running that there was anything really being transferred at all from the Faraday cage to the beam arm because of Jim's fancy yoke here. See this little picture down the bottom? He has this plastic, he likes the red shiny plastic with this aluminum L brace here. And you see these little rubber O-rings. There's several O-rings in between the plastic which holds the Faraday cage and the beam arm, which goes back into the board here. So this part here is the end of the beam arm. The power lines come through the beam arm, and this is just the power cord coming out here. So this very, very accurately, or very, very well, isolates the high frequency vibration from the beam arm, and it was done deliberately that way. In fact, I even tried to make this stuff out at peak, thinking that peak was more appropriate for a vacuum chamber, but it turned out to be heavier and clunkier, and probably not as efficient as vibration isolation than Jim's red plastic stuff. So we ended up keeping the red plastic, and it was lighter. His stuff was lighter than the peak, so we ended up keeping this. Although I have made a version in peak, just so you know, we do have a peak version, and it's slightly wider, so I could put bigger boxes in there as well. Oops, I'm moving this thing around. Sorry about that. And then we were looking at these interesting brackets. So we'd been using L brackets, just plain ordinary angle aluminum cut into a shape where we could bolt the brass reaction masses to them. You'll notice also I'm using weird kind of washers in here. So these sort of red, or not red, blue kind of washers, they're actually e-glass or fiberglass washers. And we tried several different versions of washers, because up till this point, Jim had always been using basically a rubber inner tube that happened to be knocking around in the lab. So rather than using rubber inner tube, we wanted to test different washers out and see what difference that would make. So I've got some information to show you about different washers. And also this particular slide is referring to the difference that it makes having an L bracket like this and having this interesting looking slider thing here. So this is an L bracket, but you notice this brass thing at the bottom? The brass is actually bolted to the Faraday cage. And what you're seeing here are two little rails. And this aluminum part is sitting on the rail, and it can actually physically move backwards and forwards. So it's as if I put this thing, if you can see my hands, it's sitting here and it can physically move backwards and forwards. So it's become like a free system. It's not actually bolted on one end and fixed free. It's now free. And that's what we wanted to simulate, because that's basically what you'd have in space, really, a free system. And it's the base that's actually clamped to the Faraday cage now, not the actual the thing itself. So this whole thing here can physically move backwards and forwards, sliding on these rails that you see here. There's one rail, there's another rail, there's actually two rails that it sits on. So we wanted to see if this was actually better at vibration isolation than the L bracket. So one of the tests that I ran was to shine the vibrometer here directly at the Faraday cage, not at the beam or the yoke, but directly at the Faraday cage, and see what difference it would make if I run the device with the L bracket or this interesting sliding L bracket here.
Sledge.
Yes, he calls it a sledge. Fine, it's a sledge. It doesn't look anything like a sledge to me, but I guess it's got two runners. It's a sledge. All right, fine. So let's see what difference it made. So this is just telling you, this information is just telling you how I set up the vibrometer. It was on a 100 nanometer per volt scale. I had it on plus or minus 10 volts. I was running 35 kilohertz, which is actually, that was the on resonance of this device. So I was actually running this thing on resonance using a picoscope at 35 kilohertz, and the input was 700 millivolts. And so let's see what happened when I did that. This is the actual, we're showing you that I was actually on resonance. In fact, this is a sweep from 45 down to 25 kilohertz. The blue line is the voltage applied, or amplitude of the voltage, and the red line shows the force trace. And if this is 45, it goes, since it's 20 seconds, I'm going from 45 kilohertz down to 25 kilohertz. That's a kilohertz change per second, basically. So that's 45, that'll be 40, 35. So around 35, 34, that's where we saw the interesting force pulse going on. So that's why I've got it at, I was running this thing at 35, because it's right here where you see the interesting behavior. So what happened? I'll show you what happened. So I was shining the vibrometer right at the Faraday cage. So here's nothing happening, and here's where I switch on the 35 kilohertz pulse. Suddenly it jumps a little bit. But remember, there's no isolation going on here. This is directly onto the Faraday cage. And what I'm seeing is the displacement's increasing, obviously, and but it's very small. And notice the frequency is actually quite different to the 35 kilohertz. So the background vibration I say here is 28 hertz. So that's the background frequency. And the average amplitude of this little noise here is about 0.2 microns. And then when I turned on the resonant frequency of 35 kilohertz, again, this is directly on the Faraday cage without any vibration isolation, I found a frequency of about 15 kilohertz. So it's lower. The resonant frequency was 35 kilohertz. This was 15 kilohertz with a displacement of about 0.6 microns. So it's not an awful lot. And that's using the L bracket. So that was with the L bracket. I believe I have some results here also with the sledge. So I'm just giving you a sort of a summary here of how that went. We actually had two different thicknesses. You see an 1/8 of an inch and a 1/16 of an inch. So we're using different thicknesses just to test what difference that would make. So for the L bracket of an 1/8 of an inch thick, which was the standard one that we've been using for a long time, the background displacement was 2 microns. And then when I had the resonant frequency on, it was I saw a vibration of 15 kilohertz on the Faraday cage directly with a displacement of 0.6 microns. For the thinner bracket, I found the resonance frequency shifted just slightly. It was 34 kilohertz. So again, running that, I found the background amplitude in the Faraday cage was about 0.2 microns. I hardly saw anything at all. So it seems like the thinner L bracket seemed to have better isolation properties than so I guess it oscillated a bit more itself. So it wasn't being transferred to the Faraday cage. So let me show you what happened with the sledge arrangement. So here again is the sledge. I think now you can see that the brass part is what's being bolted to the Faraday cage, and this aluminum bit, which is bolted to the device, can actually shift over these two rails that you can now see. And I believe we had some issue about the rods actually coming out of the holes. So that's why you see a little bit of red on the end. That is red Loctite. So we red Loctited one end, but it can still move backwards and forwards. It's just that we wanted to make sure the rods wouldn't come loose because they had a tendency to wriggle out of the holes. So with the sledge mount, again, I used two different thicknesses of bracket for this L bracket on the top here. For the 1/8 of an inch, I found that the frequency was about resonant frequency was about 36 kilohertz, and the background displacement about 0.2 microns. The resonant frequency, when the resonant frequency was applied, the Faraday cage was seen to oscillate at about 2 kilohertz with this sledge, and the amplitude of the oscillation went down to 0.3. So that's half of the displacement that you were seeing with the regular L bracket. So this sledge does in fact reduce the amount of oscillation that is transmitted to the Faraday cage. And with the 1/16 of an inch thickness of this mount bracket, 0.36, so maybe slightly greater, but the vibrational frequency went down. It went down to 0.123 kilohertz rather than 0.22 kilohertz. So again, it's nothing to do with the 34 or 35 kilohertz that I was as resonance. It's a smaller frequency, but and the displacement was very, very small. But again, if I were to shine the vibrometer directly at the beam, you literally see nothing at all. You see the background. Even when the thing is on resonance, you don't see anything transmitted at all because the yoke is so good at vibration isolation. So I just thought I'd mention that. I think also I've sort of said that too here. I wanted to make sure that you know that when I was doing those tests, I was testing on the Faraday cage without any vibration isolation. And so the yoke is really doing a very good job. And that should say Faraday cage. There you go. So the rubber O-rings really are doing a very good job of isolating that vibration from the beam arm, which is very important. So then moving on, what else have I got to talk about? Oh yes, thermal issues. We had many, many thermal issues. Oh yes. So one of the first things we tried to do was to put on these big fins on the side. This is what changed the calibration. I had to recalibrate after this. See this braid? The braid is going from the fins all the way over to a great big bolt, which we put through the plastic vacuum chamber here. And we can, in principle, put a braid here and put it into an ice bucket and then cool it off. So that was our cooling mechanism. Basically, it's just radiative from the fins, and then we can extract the heat through and out of the chamber using this big brass bolt like you see here. Here's a close-up of the fins. You can now see them a little bit more in close-up. They're very, very close to the central column. So that was one method. The braid that you see here is actually going to the top of the Faraday cage. So I actually had braid going to the top of the Faraday cage here, and that helped a little bit, but it still wasn't quite enough. So what we decided to do was to put a Peltier device on top of the Faraday cage and then actively cool it. So you see here some fins that I put on top of the Peltier device, and here's the power cord for the Peltier. What I did was, and I think Jim did not approve, I disconnected. I was running out of wires going in and out of the Faraday of the chamber, so I disconnected the coils and used the coil connections for the Peltier device. Oh well, whatever. So I could cool, and I could use a variable resistor and turn this thing on and off as I wanted, and I was using this lab jack thing to control the Peltier. The lab jack also controlled a little thermistor that I put between the washers, because I was also testing different washer configurations, and so this was used in between the washers just so I can get an accurate temperature of what was happening to the washers. Because I was noticing when I was removing the device, I could see some of the washers were turning strange colors. They'd carbonize, or some of them would stick together. The peak ones would stick together and clump and sort of almost melt. So I was wondering what on earth the temperature was of these things. So that's why I started using this thermistor that basically went between the washers so I could tell what the temperature was. So I just thought I'd mention that we tried to do some cooling. Oh, over here, you're probably also wondering what the heck is going on here. There's a piece of copper tape on the bottom of the Faraday cage. There's the electrical tape on the bottom of the cage to isolate it from the cage itself. And then there's a copper tape. And then, so this thing was put in, I actually put a contact on this. This is extracting heat. And so this is what's going to the braid. And that's the braid that you can see coming out along here, going to the fins. So it's inside the Faraday cage itself. I'm also trying to...
Hal, yeah. just a sec. Let me make a comment here.
Feel free to
The reason why you isolate it from the Faraday cage is so that circuit low on the power circuit is not grounded to the Faraday cage, which is its system ground, so that the return current from the device during operation goes back through the low side part of the circuit, so your twisted pairs actually work. It's not just doing it for the fun of it.
No.
Okay, sorry.
No, thank you. And by the way, when I did this, originally I didn't have this great big capacitor here. That's a microfarad capacitor. And I was getting all kinds of weird noise. I was thinking, what on earth is going on? And of course, this stupid Faraday cage was acting like a dirty great big antenna. So I had to have one of my colleagues, Paul March, tell me to put a microfarad capacitor in parallel with this thing, so it wouldn't pick up like an antenna and give me all this noise in my data. So when I put the capacitor there, the noise went away, thank goodness, and I didn't get the thing acting like an antenna pickup. So that was good news. Okay, moving on. So we try to deal with some thermal issues by active cooling and by extracting heat directly from the Faraday cage and actually cooling the Faraday cage itself. I didn't really know how to get directly onto the device without ruining the acoustics or the vibration of the device. So we thought we'd just handle with the Faraday cage. The Faraday cage does get warm. You can actually feel it, you can touch it, and it's warm to the touch. So we thought that was a good way of trying to cool. Okay, so washers. We tried a whole bunch of different washers. I tried phenolic, we tried pure PEEK. In fact, PEEK was one of the first ones I tried because I just happened to have some PEEK screws and washers lying around, thinking that my students would build another device. And I probably should mention that we do have students working on this project too. I have 2 graduate students and an undergraduate. Dave Matalan is trying to build a whole new balance beam, and he's going to be using the PEEK. And I have an undergraduate student who set up my 3D printer, which can do PEEK and does various other things. In fact, he just printed something out for me the other day, just to prove that it was working. A little CSUF thing. I don't know if you can see that. He made that in. So I know that the printer now works, and I also have another student who's helping me with the IR sensing, that sort of thing. So we wanted to have a little IR sensor sitting on the Faraday cage to look directly at the device so we could tell the temperature of the device. So I've got a student working on using lab jacks and IR sensors with the lab jack so we can get that going. I think we're going to need more leads coming into the Faraday cage. Yeah, we're going to need some more wiring into the chamber because I'm going to run out of leads with all these different bits and pieces. But we'll worry about that later. I'll have to disconnect those coils again. Shh, don't tell Jim. So we've got we tested all kinds of different washers. Here's some phenolic washers. And the first thing we noticed, of course, I was getting weird things happening with the outgassing from the threads. So Jim very kindly drilled these minute little holes in each individual washer, which I thought was way too much work. But he did. You can actually see the hole there that he's drilled inside the little washers to allow the air to escape from the threads, because I was having some issues with that. So we tested phenolic washers. We tested Vespel or polyamide washers. Again, they all have little holes in. And then when Jim got tired of drilling holes in each individual washer, we decided to drill a hole in the actual bracket itself. Now I think you can see the hole here. I'm just pointing at it here. So he actually drilled one hole, and that would work for all of the washers. So you can imagine when I was trying 5 on each side, it got a bit tedious because that's 5, 10, 15, 20, 25, 30 washers you want to drill holes in. I don't think so. So we had the hole in the bracket instead, and that worked just as well. So and then, of course, we came up with a great idea of putting the thermistor actually in this mount bracket rather than having it way over here in the end cap. So right now you see a thermistor in the end cap, but you also see a thermistor over here, and I could choose which thermistor I wanted to use. And I could also use that the one on the cable, the separate one, and put them in between the washers, which I also did, just to make sure these washers weren't going to carbonize or melt on me. So I did have some problems with the phenolic. The phenolic ones, they were not very temperature resistant, and they did tend to carbonize. And then the Vespel, they were actually quite good. You didn't have to worry about the thermal properties of the Vespel too much. The carbon reinforced PEEK were also fairly good. I noticed that the 5x5 with the carbon reinforced PEEK worked fairly well, and the 2x2, this one for a polyamide, actually worked fairly well. The rubber inner tube that Jim had been using for years was absolutely the worst one. So he was getting some really rubbishy results. So this was like 1 micronewton, and these other ones that I tried were for a factor of 10 greater in force. So, whoops. Oh, I'm moving stuff around now, so I better be careful. I'll leave that alone. So the Vespel was pretty good, 2x2, and also the carbon reinforced PEEK was pretty good. The E-glass, I think 3x3 was not bad. Let me show you what happened. I tried all of these things with the glued stacks. So the glass stacks were actually glued between the aluminum end mass and the brass. So it wasn't just the the 256 bolts holding them together. As you see here, the 256 bolts, we actually glued the stack directly to the end masses in both of these cases. And I was using the same stack over and over with an 1/8 of an inch L bracket. So I decided to use that one. People are phoning me at the wrong moment. I'm going to turn this. So I'll just turn that off. So let's see. So here's the results with the washer testing. So I was using the same 5-inch reaction mass glued stack with the 1/8 of an inch bracket, and I was using a sweep of 45 to 25 kilohertz sweep for 20 seconds with the same Rigol signal generator, and I was using a Carbon DCM 2000 amplifier on level 12 and a 4-to-1 transformer to give it a bit of a boost. Turned out the phenolic washers with 2 each side was the best arrangement, and it gave a force of about 9 micronewtons. But I did notice that the phenolic was carbonizing at high temperatures, which wasn't very good. The E-glass, fiberglass mil-spec, 4 washers either side gave about 10.9 micronewton force. The Vestal polyamide, 2 washers either side of the L bracket gave about 11 micronewtons. And that's actually very similar to carbon reinforced Vestal, which we also tested. The carbon reinforced peak, we go back one. Carbon reinforced peak, 5 washers either side was the best arrangement. That had absolutely no thermal degradations. That was a very good choice. 11 micronewtons force. And then, of course, the rubber inner tube, which Jim had been favoring for the last 30 odd years, that was the worst at about 1 to 2 micronewtons of force. So that was definitely not the way to go. It was a very good idea to try these different materials, and that did give us a factor of 10 increase. By the way, just to show you, I actually put these washers inside a laboratory oven just to see what would happen. Here's the fiberglass ones, the E-glass. You see, when I cooked it at about 200 or 260 degrees, it just went black. But they didn't really stick together or clump together or melt or anything weird, but they went black, and it obviously changes the properties. So that's maybe not the one that we want to use. The phenolic was actually worse, although it did show some good, we got some good forces with it, but as you see, it carbonized and it looks kind of nasty. So that's not gonna be a good way to go. And the peak washers, well, they really just clumped together, and you got to, that's my peak mush there, I call it. It was no longer individual washers. They literally molded together to become one big fat washer. So that was no good at all. So we decided the Vestal was a good idea, and the carbon reinforced Vestal was pretty good. But then we moved on to other things. We also tried Belleville washers, which were actually the best of the lot, but I haven't actually mentioned those here. I think they're going to be mentioned a bit later on, so I'm not going to mention those in this section. Let's see. I was also a little bit worried about center of mass shift, because now we're having this thing on this sledge, and it's physically moving a fair distance of maybe a fraction of a micron or a couple of microns. So I decided to take a look at what would happen if I actually physically moved this mass on the beam, sort of perpendicular to the beam arm. This is actually more relating to the newest type of sledge mount, which Jim is going to talk about this afternoon with the help of our NIAC team members. So this one has the greatest motion, and he's going to talk about that more. So you can see the frame of the mount here. It's actually 2 square frames, and then there's these 3 rods. Actually, there's 2 at the bottom, 1 on the top here. And then this mass now has these 3 little ears sticking out. He's going to talk about this a bit more later. So I'm just showing it to you just so you know. I took the mass out, I weighed it. This thing, the actual device, weighs 125 grams. So I put together a mass here that was 120, and then that's 5 grams that I stuck on top. So there's 125 grams. I marked it. I marked the center mark, and there's also marks on each in the center, sort of showing the central line. You see, I've got a ruler on top of this thing, and the ruler has a central line. So I aligned lines on the mass with the center line, and also the line that you see here with the marks on the ruler. So I sort of made marks on the edge so I could see it a bit more clearly. So basically what I did was to take the center position, and then down here, you can't see right now, but there's a little wire hanging down from the center. I'll show you the next picture, then you'll be able to see it. Let's see, where am I? I'm there. Come on. You see this wire hanging down from the center coil. that coil actually physically moves. These other two coils are static. So this coil can physically move left and right. So here's the center position, and I measured where the coil was at, and it was at exactly on 80 millimeters on my ruler down here. And then I took the mass and I physically moved it over 3 centimeters or 30 millimeters to the right. And then I noticed that the central coil would move to the left, and it was now at 79.5 millimeters. So the coil, the arm itself, had physically shifted 0.5 millimeters to the left when I moved the mass 3 centimeters. That's quite a big difference, 3 centimeters to the right. When I moved the mass 3 centimeters to the left, then the coil shifted the other way and it went to 80.5 millimeters. Again, this is reproducible. I did it over and over again to make sure I was seeing the right thing. So I took the this shift here, this 30 millimeters, and I calculated what the force would be due to something maybe of not 30 millimeters, but 0.5 millimeters, which is the sort of shift that we could actually see this device making in this new sledge. So let's see what happened when I did that. So so I said, well, this is going to be linear. So I've got y is equal to ax. Let's say y is 30, and then and I want the x to be, the x is 0.5, as you saw, it shifted 0.5. So the constant between the motion on the top, the mass motion on the top, and the movement of the beam arm between 30 millimeters, and it's shifting 0.5 millimeters. So the constant would be 60. So let's say the center of mass of our device moves by 0.5 millimeter. Okay, then you'd expect the wire to move by 0.5 millimeter divided by 60, which is about 8.3 microns. We've previously saw that the Filtech sensor calibration, I got 0.75 volts gives a micrometer displacement. So 0.833 microns would give a sensor voltage of about 6.2 volts, and that's roughly equivalent to 62 micronewtons. Okay, so what I found was that if a device moves 0.5 millimeters, you get an equivalent force of about 60 micronewtons. The thing is, the forces that we're seeing now are way, way bigger than 60 micronewtons. So I'm going to let Jim describe that to you later, but the most I've ever seen the thing move is about 0.5 millimeter, and that can at most give you a 60 micronewton response, but we're seeing forces much bigger than that, I think, and sometimes the motion is much less than 0.5 millimeter, so and we're still seeing much bigger forces than that. So it's not just a center of mass motion, I'm pretty sure, and I did check it very carefully. Here are some pictures that, again, I've had my students play with. This is David, a grad student, made up some pictures of this new mount. Again, I'm going to let Jim talk about this. I'm not really going to mention this very much. The springs.
Al, can you hear me?
Yes, I can hear you.
Yeah, this is Greg Mahalik. I wanted to ask, when you put that weight I was trying to get my microphone to work. When you put that weight on the balance back there, is it twisting the balance, or is it twisting so that when you put your...
Yes. Yeah. So,
all right. So it's a torque. It's not a linear displacement.
It's a torque, but I'm thinking that the displacement is so small. I think these coils are 15 centimeters away. So that's 150 millimeters away from the central column. And we're talking about a shift here, a horizontal shift of 0.5. So if you think of the angle is really, really tiny, much less than a degree. And so I'm thinking it's going to be a linear relationship. I assumed it was a linear relationship. I hope I'm right there. If I'm wrong, you can let me know. But I'm talking about a really, really small angular shift. So I assume that the displacement, this thing was going to be a linear relationship.
Okay. Well, what that also might imply is that, well, it depends on the mass movement, but as this mass slides back and forth in that cage, it's going to induce a torquing spring, almost like a torsion spring in that whole system.
Yeah, we're hoping that now we're seeing movements that we can maybe even do away with the torsional balance. So I'm going to let Jim talk about that, because he's going to tell you about the latest stuff. I just want to tell you that the test that I did, because I started to worry as soon as we had that slider thing, and I could see that I could almost sense that this thing was going to move a lot more than it did previously, because before we had it literally bolted to the Faraday cage. It wasn't really moving hardly. It was moving less than microns. You couldn't see it at all. Now I can actually get a video camera on this thing, and I can see the gosh darn thing move. So, oh, sorry, that's my phone. I can see this thing move. So I was getting more worried about the center of mass motion. I wanted to see what was the worst possible thing that could happen. And this is, I think, the worst possible thing that can happen. But I literally had to move the thing 3 centimeters to get this thing to move the coils down here to move 0.5 millimeter. So there has to be a big motion of center of mass to get a very, very small deflection.
Understood.
So just to let you know that I was worried about that, and you know, when I see results of hundreds of micronewtons, and I'm always a little bit skeptical. So I wanted to make sure I was taking everything into account.
Thank you.
I'm reasonably confident that the forces we're seeing, it cannot all be due to center of mass motion. It just can't. I just don't believe it. I'm going to let Jim talk more about this. I just wanted to let you know that I'm having my students CAD everything. They're probably going to make models of just about everything in PEEK or plastics. Actually, I've got my 3D printer up and running now, so we can do that. So we will have models of just about everything. And again, there's actually ball bearings in here, but I'm going to let them worry about that later. Talk about ears. You'll hear ears being mentioned. That's the thing, the little bits of brass sticking out of the brass mass here. And I was getting a bit slap happy with rulers. Notice that this ruler I found actually has not just millimeter gratings, it has 0.5 millimeter gratings, and that's why I put it upside down, because the 0.5 millimeters are down here and the millimeters are up here. So there was a reason for me putting it upside down. I wasn't being crazy. And I also took this whole thing and turned it physically 180 degrees upside down, and then of course you can read the ruler the right way up. So we did think about having the thing this way up, where there's one rod and 2 rods on the bottom, but if I hang it the other way up, it sort of hangs on 2 rods rather than 1, and then you can see the ruler the correct way up. I call this one wire here the Fearn vibrometer, because when this thing is being powered with 35 or 36 kilohertz, you can literally see that wire going, it sort of wiggles, and you can see something's happening. So even if the thing isn't physically moving, you can see that wire jiggling around, and it makes me feel good that I know that something's happening to the thing. And that's sort of the cheap vibrometer. You know, that doesn't cost $25,000. It costs, you know, a few cents. So it's nice to know that something's moving. And really that's all I was going to talk to you about, because most of the stuff is going to be discussed by Jim and my NIAC team colleagues this afternoon. So I thought I'd leave you on this cliffhanger, just to let you know that the forces that we've been seeing now are not the order of just tens of micronewtons, but we're seeing things of maybe 100 so micronewtons, and Jim and Paul and Chip and Michelle will discuss all the little enhancements that have been made since then. So I'm basically open for questions now, and I've stopped a little bit early, so we might even have a chance for a quick 5-minute break in between this talk and the next one, because the next talk is at 10. So are there any questions?
Yeah, it's George here.
Hi, George.
I got several questions, but with regard to the experimental procedure, when you were testing the vibrometer, were you taking account of any dispersion in the plexiglass, which might have altered the resonant frequency and the amplitude response? And also, did you do any control experiments by actually vibrating the Faraday cage at a particular frequency to make sure that the vibrometer reading through a plexiglass was confirmed? Okay.
Well, I can tell you that there was an earthquake at one point, and I did put the vibrometer on the Faraday cage when that happened, but I couldn't tell you exactly what the frequency of the earthquake was. But it was, you know, I could see that it was working. I did not test anything for dispersion of the plexiglass. I'm afraid I did not do that. And if you're asking me, did I put on a specific frequency to the beam? No, I did not. Now that you mention it, that should have been an obvious thing to do. And okay, so I still have L plates on when it comes to being an experimentalist. I'm doing my best, but I expect my colleagues, Jim, and people that know what they're doing to tell me to do these things, and they didn't tell me, so my fault. Sorry, didn't do it.
And if a more fundamental question, I missed the point where you described, I presume, how forces are transferred from this freely moving sledge to the balance.
Springs.
Springs.
Sorry.
Springs, George.
Yeah. Are there springs I didn't see, or are they built into the
She didn't point them
washer?
out. Hal didn't point them out. They're in the picture.
Yeah,
He's pointing them out now.
Okay,
With the
there those.
cursor.
that's actually the first ones that we tried were actually guitar strings from like a electric guitar. we had 3 different sizes. There was a 0.008 inch diameter, there was a 0.011 inch diameter, and a 0.014 inch diameter. They're kind of at the higher end of the strings on an electric guitar. And the ones that worked the best was the very thin one, the 0.008, and that seemed to give the best, the highest forces anyway. This is the 0.008. I think this one's a bit thicker one. This looks like the 0.011 to me.
How are those held in place?
I basically put them into these little tiny holes that John Woodland drilled for me using a 79 drill. And I believe he went through half a dozen of those things because they keep breaking and they're really fiddly to do. Little tiny, looks like very, very thin pencil lead. It's so small, you have to use a magnifying glass to see the actual drill head. So you can imagine how many of those he broke off. But there's actually 4 holes in the top of this and 2 holes here. And I managed to get some super glue and stick the little piece of wire in there. And then I was just bending it by hand and sort of letting it bend over and then cutting it and sticking it in there and super gluing it. And that's basically what I did. And I tried to get it as nice and circular as possible, because to actually calculate the spring constant is easiest when it's actually a circle. So the base from hole to hole is roughly twice the height of this arch, roughly speaking. Turns out if I make the arch higher, then the spring constant would go down or go up, I think. It actually gets worse. Although you'd think if it was a higher arch, it would be less of a spring constant. But it seemed to be, the easiest to calculate anyway was a circle. So I tried to make it as circular as possible. And that's not too bad, I think, doing it by hand. Although I was told that by my experimental colleagues that I should have made a little jig and put a screw there and bend it over the screw and to make them exactly precise. But anyway, the first few I did by hand, so I haven't made the jig yet. And then these rails, they're actually sitting, these little bearing things are inside the ears. So this thing is actually running on ball bearings, really, really tiny ball bearings. And you can literally see this thing moving around. And we have got videos that Jim will show you later of this thing physically, the actual device here physically shifting, because I have a Sony camcorder on this thing and you can really see it move, which is kind of exciting development.
Another question, if you don't, unless
go ahead.
I'm cut off.
No.
You mentioned that the cage, so-called Faraday cage, was picking up like an antenna.
It was at one point, yes.
Is there any relationship between, did you actually look at a spectrum of this noise and relate it at all to the kind of frequencies you are, mechanical frequencies you're looking at, or harmonics thereof? In other words, could there be any crosstalk between this pickup, since you're in a plexiglass container, and the forces you're measuring?
Right. It looked to me like the noise I'm talking about, when I looked at the voltage signature, it was like a fuzz on the voltage. So it must have been really, really, really high frequency. I don't think it was related to the resonant frequency at all. Jim, I could use some help here. I'm reasonably sure it was because of how it looked on the picoscope, it was literally just fuzz. So it just looked like really, really high frequency noise.
Yeah, I wonder where it's coming from.
Exactly what frequency? I didn't check it. I should have.
It's noise in the amplifier, George. We've had problems partly with that and partly with contacts. I use some Molex contacts for the power transfer from the cables to the stuff, the wiring on the balance itself. We've replaced them with Amphenol gold-plated contacts recently, and it's pretty much gone away. But you occasionally, basically our experiment kills amplifiers if you really push it. Okay.
Many amplifiers.
They don't die catastrophic. Well, they do eventually.
They do.
Yes.
Okay. Last of an, well.
George, I was just going to show you. Questions. You see this voltage line here? Yeah. Normally that should be a nice straight line, or at least a fine line. You can see all this fuzz. Before the fuzz was a lot worse when I didn't have that capacitor on there. So this is one of the ones I ran with the Faraday cage, and you see how fuzzy the voltage looks. I'm talking about this fuzz. That's what I'm picking up, and that's what but it was much worse. It was much thicker fuzz, if you know what I mean. And that's what the capacitor got rid of. But now I'm not using the Faraday cage anymore. That's completely gone. And the gold contacts also helped enormously. So I think there was some problem with the contact. Jim likes to put E6000 over everything. And when I undid these, took these E6000 off, the wire was barely hanging on. So it really wasn't a very good contact. So that was most of the problem, I think, with the power contacts.
Yeah, okay. Yeah, I can dig into that a little bit more later or offline. Last thing is, when you state, say 9 micronewton force or an 11 micronewton force toward the end of your discussion, can you relate that to the waveform? For instance, this waveform we're looking at now, where is that the peak?
George, let me handle this, please, Hal. George, what we're going to do is we're going to show you movies of data acquisition. Okay, what we've done over the years is we've brought up several picoscopes. We have one picoscope that does a strip chart recording like the one you're looking at here. Okay, that's time evolution from left to right. We've got another picoscope that does a power spectrum, a real-time FFT of the signals, both the voltage signal that's going into the device and the strain gauge that's embedded in the stack of PZT crystals. Both of those are displayed in an FFT format. And in addition to the FFT format, we have yet another picoscope which picks up both the voltage and the strain gauge signals as waveforms and displays them in real time as waveforms. We also, with that, since it has 4 channels, pick up the current sensor so that it does a real-time calculation of the power. Okay, so you get a power waveform in addition. You'll see those this afternoon, okay, movies of these displays and all that. As a matter of fact, I can show you a movie that I did yesterday, as a matter of fact. It's not ideal from a number of points of view, but from one point of view, it is very obvious. It shows the first and second harmonics in the FFT display. And as time goes on, you see the second, you see the first, you see all the harmonics moving to lower and lower frequencies. But as it comes up on that event that Heidi's showing there, what happens is the second harmonic peaks at the event and then goes away. And you see it in the waveforms as well. Okay, that second harmonic is critical with the right phase to the production of the thrust trace. Okay,
Yeah.
So you're going to see all this afternoon. Okay, and Michelle and Paul and Chip are going to tell you about all of that stuff. But we're paying attention to the sort of things that you're worried about. On the dispersion of the plastic of the laser beam, actually, for what's being measured, dispersion is not really that serious a problem. You can actually look. The Polytech vibrometer has a display where you see a picture of what the thing is looking at. Okay, as a way of tuning and pointing and all the rest of that. Okay, so the Polytech does what it's supposed to do, and it does it very nicely. It's unlikely that dispersion is a significant issue in this case. Okay, sorry about that. And I've eaten up the rest of your time, Hal. You've
No,
got
that's perfectly fine.
5-minute break.
Is there a chance for one more question yet?
Go for it.
Okay, yeah, this is, I'm Jeremiah, this is Mark over here at Falcon Space. We were just wondering, and maybe this is a simple question, but has anyone ever tried to suspend this thing vertically and just simply measure a change in its gravitational weight?
Yep, Jim
No,
used to do that.
It's not near, suspending it vertically and trying to look for changes in its weight won't work because the mass fluctuation takes place at twice the frequency of the driving signal, that is to say about 70 kilohertz. Okay, so a quasi-static measurement wouldn't show anything. Okay, it doesn't produce a net change, a time average change in the weight.
Oh, interesting.
Sorry about that. It would be neat because if it were something like that, you could do a really simple demonstration of whether it's there or not. Yes.
Also, I wanted to mention for Hal's video a problem where he was contemplating turning the entire device upside down, you could just turn the camera upside down and get.
No, let me explain what's going on there. There are 3 rods that suspend the devices that we're using now. And they are, of course, at 120-degree angles. And when we first put them together, we put them together with the single rod as the one that is in the up position. So in effect, the thing was hanging from one set of bearings and loading in the opposite direction due to gravity, the other 2. So what we decided to do, instead of suspending it by one, was just to flip the device 180 degrees so that there are 2 rods up now and 1 guide rod down at the bottom. Okay. And the reason why we did it was because in the very early ones with those arched springs that Hal showed you, what we found with Michelle's movies that you'll see this afternoon was that the device would rock. You can actually see this thing move now. Okay.
So,
You'll see that this
Yeah, one
afternoon.
quick question for you then about the way the measurement's being made. If I'm understanding this correctly, so when the mass changes, you need to push against it, and that's the job of those little springs, those half
No.
crescent.
The springs are just there to transfer low frequency forces to the measuring to the balance speed.
It does produce a steady low frequency force. That's what we were looking at on those charts when you're in resonance.
Yes, it produces a quasi-stationary thrust. Okay, and ideally, if we had Chip's amplifier that he's building for us, we would be able to lock on to the resonance and be able to make it a stationary steady force.
That would be amazing.
But it doesn't change the weight, as your suspension idea suggests. It produces a steady force, but not a weight change.
That makes sense.
We also
Okay.
know in the chart that it goes negative at some point. Is it possible for this force to go in both directions?
Yes, as a matter of fact, as you go through a resonance, what you see is it go one direction, and then it passes through the resonance, the direction changes. That's why you're seeing these wavy lines in the thrust trace.
So if it was vertically suspended, you wouldn't measure a change in its gravitational mass, but you would still measure
No,
the
because
force, right? I mean,
because
wouldn't
the mass fluctuations are far too fast to be they get integrated out. They integrate to zero.
All right,
Okay?
basically what I'm asking is if you assemble the whole device with everything you needed though, and could the whole device itself be suspended and then measured vertically as compared to horizontally?
You could measure the force in a vertical direction if you want, but you're not measuring the weight. You're measuring a force that's being generated
Right.
by this dual frequency and pushing and pulling when the thing is
That makes more
more or
sense.
less massive.
That really helps clarify things. I appreciate your time, James.
My pleasure.
Okay, Jim, I think maybe I should
Yes.
introduce Lance now. So Lance is going to be talking about propulsion results involving Kaluza theory. And he's due to start at 10, so it's like 1 minute to go. So I think we're on time. Wow, that's amazing.